Like many of us, I drive a car on a pretty regular basis. There's nothing quite like the freedom of the road, but it's not all fun and games. The list of driving stressors is practically endless. Traffic congestion, tailgaters, long waits at red lights. But one of the most annoying things I encounter are the potholes in the roads. Every time I feel the jarring impact of my car encountering another blemish in the pavement, I wonder, where is all the money that should be fixing the roads? There are numerous answers to that question, but the one that is relevant to today's topic is the money spent on the mitigation of tropical diseases. The adage, an ounce of prevention is worth a pound of cure, is an old one, but as we will see, it holds up remarkably well. In the modern era, healthcare problems that seem far away are actually closer than they appear. In 2016, the World Health Organization published a report that lists the donors involved in the fight against malaria, a mosquito-borne disease responsible for 250 million cases and over 400,000 deaths every year. The donors include all of the usual suspects: the United States, the European Union, the Bill and Melinda Gates Foundation, and many others. The U.S. government funds the lion's share of global malaria expenditures, costing American taxpayers just over $1 billion a year. The next logical question is all that money spent worth it? Malaria has little direct impact on the United States or Europe. It's a problem endemic to places with warm climates, especially in poor countries with inadequate infrastructure. The reality of communicable diseases which originate in the tropics demands attention, though, from both humanitarian and political perspectives. Poverty and disease feed off one another, both amplifying a tragic downward spiral of economic hardship, suffering, and death. Besides the healthcare ramifications, poverty and disease are destabilizing political forces, and we cannot continue ignoring such destabilizers in a world that is increasingly hyperconnected. The story of malaria is a long and fascinating one, a story that has shaped human evolution itself. The Oxford Handbook of Tropical Medicine goes as far as calling malaria, quote, the most important parasitic disease of humans, end quote. Malaria is a protozoal infection of red blood cells, transmitted to humans via the female Anopheles mosquito. Protozoa are microscopic single-cell organisms classified by biologists as the simplest eukaryotes, or animals. While microscopic in size, protozoa are much larger and complex than bacteria. Biologists classify malaria as a protozoal organism of the Plasmodium genus, which contains many species, 5 of which infect humans. More on these species later. Animals at risk of malaria caused by other Plasmodium species include birds, reptiles, and many mammal species, both primate and non-primate. The life cycle of Plasmodium, its journey from mosquito to human and back to mosquito again, is complex and will be detailed later. Malaria is a highly successful and ancient organism that has been around much longer than Homo sapiens, and with a recorded history that predates most human diseases. The fossil evidence of malaria goes back many millions of years. A handful of blood disorders, such as sickle cell anemia, are protective against malaria and are believed to be a result of the coevolution of malaria and humans. According to the Essential Malariology textbook, quote, a fatal periodic fever associated with marshes and biting insects has been recognized for almost 3 millennia. Pre-Hippocratic descriptions from Mesopotamia, India, and China are recognizable as malaria, but it was not until 1880 that French physician Charles Leverin identified the causative organism. Hippocrates, after whom the famous Hippocratic oath, do no harm, was coined, describes malaria in his books Epidemics and Aphorisms. The Romans, one of many cultures to associate swamps with lethal fever, coined the term malaria, which literally translates as bad air. Ignorant of modern germ theory, the Romans assumed, as did many others, that malaria was the result of inhaling noxious gases let off by marshes. Researchers at the British National Institute of Health describe Plasmodium as follows, quote, the malaria parasite is a well-organized, highly adapted end product of thousands of years of biological evolution, which would mark it as successful regardless of the criteria. Species of the genus Plasmodium are currently found in every group of strictly terrestrial vertebrates, and adaptive capacities have been particularly well demonstrated in birds and primates where the level of speciation is high. When one considers the complexity of the life cycle, including the necessity for adjustment of 2 decidedly different host environments, the precise combination of temperature and humidity required, plus vector and vertebrate host habits necessary to assure continued transmission of the parasite, its survival in nature alone is amazing." End quote. The current endemic range of malaria has greatly receded from its former high-latitude apex of the Russian port city of Archangel on the Arctic Ocean. It is now endemic only in equatorial, subequatorial, and temperate latitudes, but it wasn't long ago that the disease ravaged the European mainland and Britain. Historians have theorized that Alexander the Great died of malaria, as did Alaric, king of the Visigoths, who sacked Rome in the year 410 of the Common Era. Shakespeare, using the medical terminology of his day, refers to malaria in Henry V, Act 2. Quote, "He is so shaked of a burning quotidian tertian that it is most lamentable to behold." End quote. In 1623, Pope Gregory XV died of malaria, as did 6 of the cardinals and 40 attendants, who convened in the following conclave to select the next pope. Our understanding of malaria has evolved in a series of quantum leaps since the 1600s, when Spaniard Juan Lopez discovered cinchona bark being used as an anti-malarial substance by Peruvian natives. The so-called fever tree bark was later renamed Jesuit's powder and became the basis for the anti-malarial drug quinine. Since the days of bad air and Jesuit's powder, our knowledge of practically every aspect of malaria has extended to the molecular level, and many potent anti-malarial drugs have come online. Despite our depth of understanding and level of technology being applied to the issue, malaria remains one of the big 6 in terms of the infectious diseases responsible for the most human deaths per year. In 2016, the American Journal of Tropical Medicine stated, quote, "About 3.2 billion people remain at risk of malaria, and an estimated 214 million new cases of malaria and 438,000 deaths occurred in 2015." End quote. Malaria's tenacity is largely due to its ability to develop resistance to drug therapy, as well as the persistence of the environment in which it most thrives. Human civilizations beset by poor infrastructure, poverty, inadequate resources, and a hot, humid climate. Human hosts that survive malaria infection without receiving treatment can enter into a chronic carrier state in which they harbor parasites without exhibiting signs and symptoms of malaria, a condition known as premonition. Additionally, 2 of the Plasmodium species have the capacity to lie dormant within the liver, surviving drug therapy to emerge later in the same host as relapsing malaria. As previously mentioned, malaria is classified as genus Plasmodium, which contains many different species of malaria, 5 of which infect humans. Differentiating these 5 species is a practical endeavor and not just academic trivia. Some species are more virulent than others, and drug therapy is dictated by the type of malaria involved. Of the 5 species of malaria which commonly infect humans, 4 of them are purely human species, while the 5th has in recent years crossed over from the macaque monkey in Southeast Asia, particularly in Malaysia. The 4 classic human malaria species are Plasmodium falciparum, Plasmodium vivax, Plasmodium ovale, and Plasmodium malariae. The 5th and most recent addition to the species list, infecting both humans and monkeys in Southeast Asia, is Plasmodium noelisi. It is common convention to abbreviate Plasmodium when discussing malaria. For example, Plasmodium vivax becomes P. vivax, and so forth. Note that there are at least 5 other so-called monkey malarias besides P. noelisi capable of infecting humans, but these are rare. The endemic range of malaria is dependent on the species. The distribution of P. falciparum is extensive, occurring practically anywhere that malaria is found, though it predominates in Africa, Papua New Guinea, and Haiti. P. vivax also has a widespread distribution, particularly in Central and South America, North Africa, the Middle East, and India. It is rare in West Africa due to the absence of the Duffy antigen on the red blood cells of the locals. Like the sickle cell trait, this is likely another human genome adaptation to malaria. Northern China and North Korea are home to strains of P. vivax with long incubation periods and 10 to 12 month long intervals between relapses. P. malariae occurs mainly in West Africa and, more rarely, in the Philippines, Indonesia, and Papua New Guinea. P. ovale is common in tropical Africa and New Guinea and rarely found elsewhere. P. noelisi is exclusive to Southeast Asia, primarily Malaysia. When describing malaria species, they are conventionally classified according to the following 2 groups: the lethality of the organism and the potential for the organism to cause relapsing malaria, that is, the return of malaria in a patient in which all infectious organisms were thought to have been eradicated. The mechanism behind relapsing malaria will be detailed in the Plasmodium cycle description. P. falciparum is by far the most lethal of the different malaria species. It kills mainly small children in sub-Saharan Africa who have not yet developed an acquired immunity. In terms of lethality, clinical malaria cases are categorized as benign or severe, which are synonymous with uncomplicated malaria or complicated malaria, respectively. P. falciparum very often causes severe malaria. P. vivax and P. noelisi are also known to cause severe malaria, but the incidence of this is much less frequent than P. falciparum. The two other species, P. ovale and P. malariae, are classified as benign malaria, though they may be lethal in rare cases. Relapsing malaria, the return of the organism into the bloodstream from dormancy in the host liver after the infection was thought to have been wiped out, is possible in both P. vivax and P. ovale. A skilled microscopist examining well-prepared thick and thin blood films can determine both the presence of malaria as well as the specific Plasmodium species. This is the gold standard of malaria diagnosis. Rapid diagnostic tests, or RDTs, can tell whether or not a patient has malaria, but their ability to discern species type or severity of the infection can be limited, depending upon which particular RDT is used. Microscopy, while being the gold standard, requires electricity, so RDTs should always be kept on hand in the event of a power outage. The classic clinical sign of malaria is intermittently spiking fever. Different species tend to present with different fever patterns. This has been recognized since at least the Roman era. P. malariae fevers tend to recur every fourth day and is commonly referred to as Quartan malaria. P. falciparum, P. vivax, and P. ovale fevers tend to recur every third day and are thus referred to as tertian malaria. P. noelisi usually exhibits a quotidian or daily fever spike. P. falciparum sometimes exhibits a quotidian pattern as well, though it is technically a tertian class malaria. This is because the P. falciparum organisms can be replicating along two tertian cycles that are out of sync with each other. Quartan malaria is thus a 72-hour cycle, tertian is a 48-hour cycle, and quotidian means a 24-hour cycle. Note that in any malaria infection, periodicity may not manifest due to asynchronous infections. Ancient Roman writer Aulus Cornelius Celsus wrote the following passage about the various types of malaria. Quote, "Now quartan fevers have the simpler characteristics. Nearly always they begin with shivering, then heat breaks out, and the fever having ended, there are 2 days free, thus on the 4th day it recurs. But of tertian fevers there are two classes. The one, beginning and desisting in the same way as quartan, has merely this distinction, that it affords 1 day free and recurs on the 3rd day. The other is far more pernicious, and it does indeed recur on the 3rd day, yet out of 48 hours, about 36, sometimes less, sometimes more, are in fact occupied by the paroxysm, nor does the fever entirely cease in the remission, but only becomes less violent." End quote. The preceding passage is describing P. malariae in the first section on quartan malaria, then discusses P. vivax and P. ovale in the next session, finishing with what appears to be a description of P. falciparum, also referred to in other literature as malignant tertian or pernicious tertian malaria. This concludes part 1 of malaria.